All right, let's talk about two things that feel like they shouldn't mix. Calculus, which is all about precision and exact answers, and chance, which is, totally unpredictable. But what if I told you that we can actually use the rock-solid rules of calculus to predict the future? It's pretty wild.
It really does sound like a contradiction, doesn't it? How can you use a perfect science to measure something as messy and random as uncertainty? Well, it turns out calculus gives us this incredibly powerful tool to do exactly that. And it all boils down to one big, surprisingly simple idea.
That's it. Seriously, that's the whole secret right there. Just imagine you have a graph that shows all the possible outcomes of something. Well, the probability that your specific outcome is going to happen is just the amount of space, the literal area, under that curve between 2 points. We're basically coloring in the odds.
Okay, so if probability is an area, the obvious next question is, how do we measure that area? For that, we need a special gadget from our mathematical toolbox. It's called the probability density function, or PDF for short, and it is the engine that makes this whole thing work.
So, what is a PDF? Think of it like a map. It's a function, f of x, that describes how likely any given outcome is. Where the curve is higher, the outcome is more likely. But the real magic happens when we bring in the best tool calculus has for finding area, the integral. And here it is. This is the formula that ties it all together. It just says that the probability, the p, of something happening between point A and point B is the integral, or the area under our PDF curve, from A to B. This thing is like our Rosetta Stone for translating chance into the language of calculus. Let's just quickly break this down so it's not so intimidating. That big, curvy symbol, that's the integral sign. It just means find the total area. The f of x, that's our probability map we just talked about. The dx tells us we're adding up the area of a bunch of infinitely tiny vertical slices. And the whole thing gives us p, the exact probability we've been looking for.
All right, theory is one thing, but let's make this real. We're going to walk through an actual problem from our study guide, figuring out the chances of a specific wait time. So here's our mission. We've been given this specific PDF that models how long people have to wait. Our job is to use it to find the exact probability that our wait will be somewhere between 0 and 10 minutes.
So we just follow the recipe. First, we set up our integral with our bounds 0 and 10. Then we integrate the function. Then comes the evaluation step, where we plug in the 10 and then subtract what we get when we plug in the 0. And here's a super common mistake to watch out for. Anything to the power of 0 is 1, not 0. Once you remember that and simplify, you get this really neat answer, 1 minus 1 over e.
And when you pop that into a calculator, boom, you get 63.2%, a perfectly precise answer. So we now know there is a 63.2% chance that our wait will be less than 10 minutes. We've just taken a vague, uncertain situation and nailed down a concrete prediction. Pretty cool, right?
But wait, there's more. We can do other things with this. Knowing the probability of a range is awesome. But what if we wanted to know the average wait time over the long haul? Well, calculus can do that too. And it only takes a tiny little change to our formula.
Okay, look at these two side by side. The formula to find the mean, that's the Greek letter mu for average, is almost exactly the same. The only difference? We just slip an x in there and multiply it by our function. This x basically gives more weight to the bigger outcomes, which is, well, it's exactly how you calculate an average. So when we use this new formula and run the numbers, it does require a slightly trickier integration technique, but the principle is the same. The answer comes out to be a clean 10 minutes. So even though there's a 63.2% chance your wait is under 10 minutes, the average wait time is exactly 10 minutes. So we've gone through the formulas, we've worked out an example, but let's just pull back for a second. What's the big picture here? Why is this mashup of calculus and probability actually so important? At the end of the day, this is what it's all about. Calculus gives us a language to describe the random patterns all around us in the real world. And that integral, that's what lets us turn that description into an actual concrete prediction. Suddenly, the area under a curve isn't just a shape in a math book. It becomes a real forecast for things like how long a machine will last, where a stock price might go, or, like we just saw, how long customers are going to have to wait in line. And that really brings us to the final thought I want to leave you with. These ideas are used absolutely everywhere, in physics, finance, you name it. So the next time you're looking at something totally random and unpredictable, ask yourself, I wonder if there's a hidden curve that describes this. And could a little bit of calculus help me see the future?